Professor Hanson also is a great lecturer and with us. You guys enjoy.
Okay,
so it's all yours. All yours.
Thank you, Professor Law, for those kind comments. So, one of the themes of these the lectures that Professor Law has organized is laser diagnostics. The aspect of laser diagnostics I want to communicate are what I'll call quantitative diagnostics, meaning that we're attempting to be quantitative about the species, the temperature, the properties of the measure. And that's because I want to have a link to chemistry. So intentionally call this quantitative laser diagnostics, motivated by Western chemistry and propulsion. And this set of 15 lectures will really have three things. Underlying all of this quantitative spectroscopy is molecular spectroscopy. We have to understand something about quantum states and the governing rules for spectroscopy through the molecular parameters. And then I want to introduce you to two of the most powerful methods, laser absorption and laser fluorescence, both of which have the potential to be quantitative. And then I'm going to sprinkle throughout all of my talks applications ranging from different kinds of engines, shock chemistry. So today, right now, we're doing lecture one. Lecture one is going to proceed in two parts. We're going to give you a bit of an overview, and then we'll begin to talk about more serious material in the introductory material. So the two-part lecture. Okay, now let's see. What have I done? Try and close that up here. So let's see. So Stanford has built a new encryption system. I think I'm in violation of the rules. So that's probably what's happening. Okay, maybe this is, it could be okay. But anyway, if strange things pop up, it's because I'm in violation. All right, so this is a picture, a photograph of Stanford University. Work as the famous Hoover Tower, the landmark of the university. If you're not familiar with our university, you've seen Golden Gate Bridge. We're located about 30 miles south of San Francisco in the peninsula area of California. Okay, what I'm going to do now is just give you an overview of today. We're going to begin to introduce you to some fundamentals of molecular spectroscopy, the emphasis of laser absorption, laser fluorescence, talk about shock quite a bit, and I'm going to give you lots of examples. So that's kind of one slide. So how many of you have had any kind of a course in spectroscopy? That's nothing. So it's probably 20%. So spectroscopy is really based upon the idea that molecules and atoms reside in quantum states. And we can have transitions for emission or absorption of light between quantum states. So really, we might say that spectroscopy is the interaction of light with matter. In our case, that is yes. Here's one quick example. So this is a plot of the fractional transmission of light. As we scan the wavelength over a region that's 2300 to 2700 wave numbers. Frequency units 1 over lambda. So this means at 2500, that's 4 microns right there. And so if you look at scan this laser across this sample of hydrogen bromide, you would find that absorption of light takes place at very discrete locations. And we need to understand this. So there's a link to quantum mechanics that describes why we see absorption of light at very discrete wavelengths and why they form this pattern of lines. These are called absorption lines. Well, we're going to look at emission, and this is an example of an emission spectrum taken in my laboratory course about every year, looking at the emission from high temperature air. So we might heat some air and by plasma or combustion and look at this spectrum. So this is now emission in the vertical direction versus wavelength in the units you might understand nanometers. And again, what do you see? You see a pattern. There's a pattern of features. In this case, the spectral resolution is not sufficient to see individual lines, but you can see these grouping of lines and they form a pattern. So So there's a lot of patterns in spectroscopy that we use to try to understand the spectra that we're observing and to help us understand the quantum states that are involved so that we can specify the probabilities of absorption and emission that are needed to make things quantitative. Now, why do we care about lasers? So lasers were invented around 1961, about 50 plus years ago. Until then, people would use other light sources, or they would collect light and record. You can have your usability to record on film, and they would record on photodetectors. So it's been a progression of how spectra are recorded. Well, we like lasers because they are monochromatic, they're powerful, they're intense, and because of the intensity, we can study both linear and nonlinear processes. So I'm going to focus on absorption and laser-reduced fluorescence, which are so-called linear processes. But nonlinear processes require that we have strong electromagnetic fields, and so lasers give us that potential. This is, and I don't know if you'll be able to read this, so you don't have to really read it. I can explain what we're seeing. This is a plot of the min detection limit here, in parts per million versus temperature from around 1,000 to 2,000 degrees for different species. And what it's going to show you, if you can read, would be that by absorption of light, we can detect parts per million of these species. And this is an example of what we would do in the shock tube. We try to detect 1 or 10 or 100 parts per million of some species as a function. All right, this is just an example. Now, another way to illustrate the power of lasers is to look at a variety of different applications. So we could be interested in remote sensing of the atmosphere, we could be interested in combustion, we could be interested in laboratory studies, process control. There's a lot of applications of spectroscopy. In fact, some of my students have now started a company to look at analysis of breath from babies using the same absorption principles that we use for combustion. So spectroscopy is a powerful quantitative tool. For combustion, we're mostly interested in species concentrations, temperature, pressure, density, velocity, mass flux. Those are the properties that we're usually most anxious to record. This is a picture of our student, Mark Allen, 1986, so 30 years ago, was when we first began to do a method called planar laser-induced fluorescence, or PLIF. And he was measuring the spatial distribution of OH in a laboratory spray flame. So this was the first time that PLF had been used on a spray flame, and the picture on the monitor in the back is the distribution of OH in this way. So kind of a historic picture for me. But over time, we've looked at a lot of different systems. I've got students working in coal gasifiers. That was at the University of Utah. We also down in Alabama. We've looked at squirrel burners for the process industry. Well, petroleum process industry, they had students go to the coal-fired power plants. So we can use these techniques in the laboratory, or we can take them into the field and try to manufacture. So the spectroscopy is the same. The engineering, so here's some incinerator work that we did. So these are just examples to show that we can study everything from very small experiments in the laboratory to large experiments in the field. Now, not all the laser techniques are as portable as others. We have some that are portable. Students will pack up 3, 4, 5, 6, 7 suitcases and take the techniques on the road. In fact, I've got students who are in Houston right now. I'd like to argue for the impact of optical diagnostics in multiple ways. We might be interested in characterizing large test facilities. This is an example of the scramjet test facility at Wright-Patterson Air Force Base in Ohio. Very large, so one of my students is right there. So there's the possibility of using lasers to look inside and to characterize the performance of these high enthalpy complex test facilities, just to understand what's happening inside, what are the properties being generated. This is a supersonic flow, so what flows are being generated by this large tunnel. Other times we're looking at reactive environments such as this pulse detonation engine, where we really are not even quite sure what the chemical processes are. And that's an example of something that was done in the desert of Southern California at the Navy's test center. I had one student who tried to apply this method at the exit plume of a Type 4 rocket at Aerojet in California. So these are basically characterizing facilities, or even just trying to achieve some understanding of what these flow fields are like. Other times we understand the flow fields and we're trying to validate CP models or produce a database which can be used for such purposes. Example here, we're looking at a cross-section of an instantaneous plot of image of temperature in a jet crossflow, a jet of hydrogen going in and mixing with a left to right cross-stream high temperature. Or we might go inside an internal combustion engine and try to make measurements inside. So the physics is the same, the engineering is a little different, but this is the power of spectroscopy to look at both fundamental studies and also in engineering applications. Applicable to large-scale systems as well as laboratory science. Okay, now one of my favorite tools is a shock tube. This is a long tube, typically constant diameter, typically separated into two sections, a high-pressure driver section and a low-pressure test section, filled with the test gas of interest, separated by a diaphragm, and the diagnostics are typically down near the end wall, might be comprised of a number of different lasers being used for absorption, or we might be looking at measuring pressure or infrared or UV emission. In application, the pressure difference across this diaphragm causes a shock wave to form, and if everything was working well, the shock would form at about 10 diameters and then proceed at a nearly constant speed down the shock tube. So you know from the course you will hopefully have had in compressible gas dynamics, if you know the Mach number of a shock wave, you can calculate the post-shock conditions very accurately. So we measure the speed of this wave, and then when the shock wave reflects, the boundary condition is that the gas must come to rest. So behind that reflected wave, the gas is stagnant. And that's a very nice situation for studying chemistry. Essentially, it's a homogeneous reactor, which might last for from 1 to maybe 20, 30, 40 milliseconds of time. We can probe that reactor, so it's a transient reactor. So that's a typical experiment for chemical kinetics. So there's the shock wave getting behind this stagnant sample of gas, which can undergo reaction at, but we might know the temperature and pressure better than 1%. And the time scales might range from a few microseconds to a few tens of milliseconds. So the advantage of the shock tube concept is that it's a nearly ideal test platform. So if you want to produce 1500 degrees K gas, you can do that. I've got one student who's working producing 10,000 degree air, to study the chemistry of air, but we also do experiments at 500 Kelvin. So we can vary the speed of the shock wave, and therefore the temperature balance that we impose on this gas, produce more or less any temperature we want. Typically, these pressures might range from a fraction of an atmosphere up to hundreds of atmospheres. We can vary that also. So this is a virtue of this relative to other devices is that we have a very clearly defined time zero when the shock wave passes our observation board. The shock wave is nearly planar. We calculate these properties very well. And by making the diameter of the shock tube large, it might vary from, say, 4 to 5 to 6 inches. By making that diameter large, we have a long path. And that optical path is where we get our signal. We'll measure the attenuation of light along that path. So, of course, if you double the path, you get twice the absorbance. That's the virtue. So that's the idea. We can use these shock tubes in a variety of different ways. We can study the ignition delay time, which is an engine parameter that people care about. So you shock heat the gas to some specified temperature and pressure, and you're asking the time it takes before it ignites. Or we can study elementary reactions. We might ideally look at a very specific gas-phase elementary reaction and measure the rate coefficient. This would be the way that for temperatures above, say, 1400 Kelvin, it would be the established way to measure chemical reaction rate constants. Lately, we've been trying to push this down to lower temperatures of 600, 700 Kelvin. So it's a very versatile, variable temperature device. What's the problem? The problem is that this is a transient phenomenon. So we have to make our measurements accurately and in short time. What we aspire to do typically is to measure species time histories in a nearly isothermal environment. From those time histories of critical species, we infer the reaction rate coefficients. So those are the type of things that we can do. And over time, we've learned how to measure quite a few different species, reactive radicals such as OH, intermediate species that are formed when hydrocarbons decompose, such as methane and ethylene. and combustion products, CO, CO2. So those are the species that we are interested in, and over time we've learned how to measure quite a number of these things. Okay, so that's a little bit of background. I want to show you some representative data. Now, this is a very important data set that we acquired maybe 4, 5, 6 years ago. This is the mole fraction in parts per million versus time in microseconds. If we shock heat 300 parts per million of heptane in oxygen with equivalence ratio of 1 at 1500 degrees Kelvin, 2 atmospheres. So what we see is that even after 10 microseconds, there's no longer essentially any heptane. We've instantly converted that heptane to ethylene. Now we see the ethylene on the way. You see the OH radical coming up and going down, coming up and going down, combustion products. So this was really the first time that we measured in one experiment multiple species. And when you see these species time histories, you begin to realize you can probe different phases of the combustion reaction. So we start with heptane and oxygen. It's at 1500 degrees Kelvin. What happens? Well, you know eventually what happens is it forms CO, CO2, and water. Yeah, but how long does it take? What are the chemical species that are formed in between? And that's the information we use to test or challenge the detailed reaction mechanisms being developed by various groups around the country, around the world. This is a particular comparison with JetSurf 2.0, which was produced by the people at Southern California. What you'll see is that the data are in the solid color, the dashed lines are the model. So if you look at that, everything's semi-log plot. So we see basically generally good agreement, especially for CO2 and water, but some difference here that's greater than our experimental error. So what I'd like to argue is by looking at different species and at different times, you look at different parts of the chemical mechanism. So you're able to interrogate and evaluate the many different reactions to turn into experiments. This is like the state of the art, how we study combustion chemistry and shocking. But the gold standard experiment is one in which we study one particular reaction. So if you've had any course in combustion chemistry, you'll know that this reaction, H plus O2 going to OH plus O, is generally called the most important reaction in combustion chemistry. Because it's a branching reaction that converts one radical to two. This is the most, if you do a sensitivity analysis of the ignition delay time, some gases, some fuel, and oxygen mixture, you frequently find it's the rate coefficient of this reaction that is the most important parameter to get correct in modeling ignition delay. So the gold standard experiment is, well, let's measure that rate coefficient by itself in the absence of other competition. And so we've done that in this experiment. So these were experiments by one of my students in 1990 using OH laser absorption. These red ones are more recent experiments about 5 years ago, which we measured on other species. What you'll see is that these data points have very low scatter, and they fall on a straight line, which is called the Arrhenius line. And that they are superior in terms of scatter to the method called the HRS that's used by some other people. So that would be a gold standard experiment. Determine that rate. It's like determining a thermodynamic property. You determine it, it's done. It's forever. So it's like producing a database of fundamental reaction kinetics. All right, so I'm kind of at the transition point now. I've included in these notes, which you have access to, a list of useful textbooks that might be of interest. Now, this is just to remind me that my textbook on spectroscopy is out at the end of this year. I've been doing this course over about 35 years of my notes. So finally, this is going to come out. All right, so here's our schedule. 5 days, 15 lectures. We're in number 1. Here we're going to do an overview. We're going to transition into some fundamentals of spectroscopy in a minute. And so this is just the outline. It's very easy to know. So we'll talk about some fundamentals of diatomic molecules today, this morning. Then we'll move to tomorrow morning. We'll talk about polyatomic molecules. And then we'll move on to some aspects of absorption and fluorescence and line shapes. Then we'll go back to electronic spectra, and then we're going to do some case studies, and this is kind of a divided line here. The rest of the course will be on applications of different kinds. So we need to understand the spectroscopy, we need to understand the positions of lines. Where do molecules absorb? Where they absorb is where they emit. What are the wavelengths at which they absorb and why? How do we calculate this? That's the positions of lines. We also have to understand the strengths of lines. How strong are these features? What's the probability of absorption? What's the probability of emission from a given quantum state? And then there's also the shapes of lines. So even though these lines that we calculate will have a discrete, specific wavelength, they actually have a little bit of width. And that shape turns out to be important to us. We can actually learn something from the measured shape of the line. So there's positions, strengths, and shapes. Those are like the elements of spectroscopy. Okay, so now that's all background. Now we'll start talking about more specific things. And quantum mechanics is the foundation. But you don't actually have to have a course in quantum mechanics to do spectroscopy. So we save a lot of time, and especially in this short course, by proceeding, and all we have to do is accept a few, very few rules for quantum mechanics. Talk about Planck's law, emission, absorption. And we'll give you some examples. So there's something called Boltzmann statistics. So how many people have any idea what Boltzmann statistics means? Hopefully at least half. Okay. So there's this, you will have heard of kinetic theory, you'll have heard of statistical mechanics, chemical thermodynamics. These are kind of like the foundations of thinking about molecules in combustion. So in the distribution of molecules over there, a lot of quantum states, populations are given to us by Boltzmann distribution that effectively determines the temperature. Or we can take the distribution and get the temperature, or with the temperature we calculate the distribution. This is a picture of one of my students using a laser that we've had for quite a long time. Typical laser laboratory that produces monochromatic light. So one nice thing about a laser is you can have a tunable laser, you can produce essentially any color or wavelength that you need. So you want, if you know the line position that you want to hit, you know what laser to use, and the lasers can be very narrow and can be precisely located. Okay, so Planck's law, the role of quantum mechanics and Planck's law. What do we need to know from quantum mechanics? Quantum mechanics tells us that when we have molecular or atomic systems, that these microscopic particles must exist in some quantum states. They cannot have, they must follow certain rules. They're only allowed values of angular momentum and energy, and these are called quantum states. They're quantized. And so this would be a picture of a potential energy distribution for diatomic molecules. So you have a picture, we have a nitrogen molecule that's vibrating, rotating, translating through space. So this horizontal axis would be the internuclear spacing. And this vertical axis would be the potential energy that's stored in the spring that connects these two nuclei. So this is the minimum, that's the equilibrium position of the molecule. So if the molecule is very, very cold, it's nearly constant in its internuclear spacing. But this vertical direction is potential energy, and we have to worry about three types of internal energy. We separate the internal energy from the translational energy. The center of mass of the molecule is moving through space with kinetic energy. We don't care about the kinetic energy. It's the internal energies that are quantized that we care about. So that internal energy can be thought of as separated into components of electrical, electronic, vibration, rotation. So we're going to be mechanical engineers, so we're going to visualize this molecule as a solid mass of nuclei, massless spring. We're going to think about classical mechanics, and then we impose 2 or 3 rules from quantum mechanics. So this is a classic diagram of potential energy. These horizontal lines correspond to the amount of energies comprised of these different components. If you see a well like that, that means we're in one particular electronic state. These horizontal lines now show us the measure of the rotational and the vibrational energies. So, think about this molecule, a diatomic molecule, usually a heteronuclear diatomic molecule, meaning that the 2 nuclei are different, or a homonuclear one which are the same. And so we take our mechanical model and we imagine that there's some sort of massless spring, and this thing's vibrating, and it's also rotating, and it's translating through space, but we don't care about that. So that's our model. And we're going to find that if we take that model and then approach just a couple of rules from quantum mechanics, we can calculate the positions of the lines that we're interested in. Now, the role of quantum mechanics is Planck's law. So if we are existing here in a quantum state that has this much energy, there's no meaning now to the horizontal axis. vertical direction of energy. If we're residing in this quantum state, if we undergo an absorption of light, we go to a higher quantum state. If we undergo a spontaneous emission of light, we go to a lower quantum state. And we can only go where quantum mechanics allows us to go. So quantum mechanics will impose on us that energy levels are quantized and that only some energy levels can talk to each other. Really simplifies things quite a bit, but we just accept this. Because these energy states are quantized then, that means that the spectrum that we observe is quantized, discrete spectrum. So we'll only see lines at certain places. We'll call them lines. Those are so-called allowed transitions. Planck's law says that this conservation of energy law, it says that the difference in energy between the upper state and the lower state is h nu. So you will have heard probably in physics course the duality, the dual nature of radiation. You can think of it as photons and energy, or you can think of it as electromagnetic waves. They're equivalent. So this is the relationship between them. It says the difference in energy between these states, which is quantized, is h nu, where nu now is the frequency in hertz, and h is Planck's constant. So this says that the difference between these two states corresponds to a frequency of electromagnetic wave. But that's also the energy of the photon. So this is expressing this dual nature of radiation. Now, spectroscopy, people tend to specialize in one spectral domain or another. The UV spectroscopists are probably different than the microwave spectroscopists, or different than the infrared spectroscopists. They have somewhat different units sometimes, and that can be a little confusing. So I'm just showing you there are some differences here. So we have available to us this important relationship here with c, lambda, nu, speed of light, wavelength, and the frequency. So wherever there's a nu, we can substitute c over lambda, and 1 over lambda is the frequency in wave numbers. So nu bar, or 1 over lambda, is an energy unit in wave numbers. So you might see this equivalent Planck's law in different forms as we deal with different kinds of units. Frequencies, or wave numbers, or wavelengths. Now if you're a small molecule, such as NO, CO, CO2, and so on, H2O, small molecules have these discrete lines, and they tend not to overlap. So it really looks like a discrete spectrum. If you go right over to a bigger molecule, like hydrocarbon fuel, say heptane, or detonate, then those large molecules have such closely spaced energy states that it looks like a continuous distribution of absorption. So we call those blended features. So there really are small molecules or discrete spectra, large molecules have blended spectra. Okay, so we're going to talk about absorption and emission. You will hear in a diagnostics lecture people talk about Raman spectroscopy, Rayleigh spectroscopy, Carr spectroscopy, laser-reduced incidence. You hear a lot of terms. They're based on the same physics, except some of those processes require work on the power law of the intensity of the electromagnetic intensity, electromagnetic waves. We're talking about linear methods, which means everything's proportional to the strength of the electromagnetic wave. Okay, so we might talk about absorption, fluorescence, emission, scattering, different types of spectroscopy. Absorption. Absorption is governed by Beer's law, and we're going to derive this Beer's law a little later in the course. In this concept, light coming from the left, there's an intensity I, where those units might be watts, or watts per unit area, or watts per unit area per unit spectrum, different units, but some form of intensity or power, and frequency nu, passes through an absorbing gas. The light that comes out is diminished in intensity, and it's a transmitted intensity I sub t. So the question is, what's the ratio? What's the relative value of I t to I? That's going to be given to us by the law that I call Beer's law. It sometimes goes as Lambert-Beer's law, or Lambert-Beer-Gay law. So discovered in different countries in different ways. But if you do this and you imagine that you vary the wavelength of this frequency of this beam, you would see these dips in transmission. So transmission might be one, and here's a line, another line. And you can see this pattern if that molecule absorbs light in this wavelength. This law, the ratio, fractional transmission, T sub lambda, is an exponential decay law. And that quantity there in the argument is called the absorbance. And the absorbance is expressed typically in two forms. It's either expressed as the number density of the absorber cross-section for the process and the path length L, or it may be written in terms of some other parameters, the SP, chi, phi L. I'll talk about that in a minute. So the point being that if you double the length, you'll double the absorbance. Cross-section might be zero if there's no absorption, or it might have a maximum value. And obviously, if you double the number density of the absorber, you're going to double the absorbance. So it's a linear law. That's the form that we use when we're dealing with big molecules. If we're dealing with small molecules with discrete spectrum, we tend to use this form. And I'll introduce you to these parameters later. For instance, the strength of the transition, E is the pressure, static pressure of the gas, chi is the mole fraction. So taken together, there's the partial pressure. P is the line shape function of length L. So that's Beer's law. It's the governing equation which we'll derive later for the absorption of light. Okay, I've already told you that I like to think of the components of spectra being lines. So when those lines form into certain patterns, we call those patterns bands. And when those bands form into certain patterns, we'll call that grouping systems. So there's segregation of terminology. So if we have transitions between electronic states in molecules, all the lines between those electronic states comprise a system. If we look at simply the transitions between different vibrational levels, and all of those lines, that's called a vibrational band. And then that's comprised of many, many lines. So there's a lot of terminology in spectroscopy that you have to get used to. Spectroscopy is terminology and accounting. A lot of accounting, keeping track of it. So we're back to this diagram. When you see this thing, this is the potential well for one electronic state of a diatomic molecule. And now I've plotted this as the distance between the nuclei. So this is the minimum. That just means that when this molecule is vibrating, if you pull it apart all the way, it becomes two atoms. If you let them come together, they'll come together with this amount of potential energy. You get closer and closer, they attract each other, and the potential energy is going down. And so now as it's going down, conservation of energy applies, so what's happening is transferring this potential energy of electromagnetic attraction to kinetic. So if this two atoms come together on a line, say, they come together, they'll pick up speed as they convert potential energy to kinetic energy. And then they'll keep going toward each other, and then they begin to repel. So they'll come in up here, and then come down, and then they'll go back up to about here, and then go back out again. So it's this conservation of potential electromagnetic attraction energy and kinetic energy. If the molecule undergoes a collision while that's taking place, if these two atoms undergo some sort of a collision while this process is taking place, they're going to lose some energy and they'll get trapped in this well. Or if you start with a molecule like nitrogen or CO, it's at room temperature, it's resided down here. You have to add all of the dissociation energy to pull it apart. So it resides down here, and then we have to pay attention to the fine structure of the rotational energies and the vibrational energies. So remember, internal energy is comprised of three parts. If we're only dealing with rotation and vibration in one electronic state, we're just down in here. Okay, so components are lines, bands, and systems. If we think about, here's an individual line that we might observe. If, however, we scan over a wider range, we might see a pattern that looks like this. So now what I'm plotting would be essentially the group of lines that correspond to a transition between one vibrational level and another. So we've got vibrational quantum numbers, rotational quantum numbers. We're in some quantum state down here, and if we undergo an absorption, we go up here, that would be a row vibrational transition because we've combined change in rotation and vibration. When we do that, we see a pattern of lines. And that's a band. That's the band of all the lines between this vibrational level and this one. they tend to group into pairs, and those are called branches. So we'll find that there's an R branch and an E branch, and I'll tell you what that notation is later. So those lines now are grouping into branches, which taken together form a band. And this distribution of absorption intensity is nothing more essentially than a mirror of the Boltzmann distribution states. If you give a temperature, you can calculate the population fraction in any given quantum state. So if you increase the number in a given quantum state, you increase the absorption. But it's a temperature-dependent pattern. Now, if you're residing down here in the low vibrational level, because you're nearly room temperature perhaps, you actually can undergo vibrational change to this next level, or 2 levels, or 3 levels. And those, therefore, would correspond to different bands. So here's this band that corresponds to all of the lines with a delta V of 1. So if we go from V equals 0 to V equals 1, all of those lines have a delta V of 1. And they're the ones that form this grouping of a band, which is comprised of two branches, which is comprised of many lines. But if we go from V equals 0 to, like all the pointers are done, if we now have V equals 0 to 2, that would be what? Roughly twice the energy, which would be roughly half the wavelength. And that grouping would be called the delta V of 2 band, and the delta V of 3 band. So they're widely separated. There are names for these bands too. The point is, we start from one vibrational level in many rotational states. We have lots of choices. Now, systems. So I talked about bands, and I'm going to talk about systems. If we look at nitrogen, nitrogen would have multiple possible electronic states. The ground state is denoted by X. The excited states might be denoted by A, a B, and a C, and some notation that we'll learn about. That's the C3 pi state. This one here is the A3 sigma state. So the quantum mechanics and spectroscopists have developed this very compact semantics or terminology to tell you properties of the state that you need to understand in order to do quantum mechanical calculations. We're not going to do that. We just accept these labels. And there's a meaning for each of these terms that we'll talk about later. It turns out that when you heat nitrogen in a laboratory with plasma of some kind, you will see lots of emission or absorption of lines between the A state and the B state. That grouping has been called the first possible system. So people observe things, they give them names. Over time, people accept the names. So the grouping of lines that corresponds to transitions up to the C state, that's called the second possible system. It's just semantics and terminology. You don't need to understand that right now. It's just semantics and terminology. So why am I showing you this? If we were looking at electronic spectrum, we're changing the electronic characteristics between this state and this state. The difference being that the electrons have changed their orbits so that the energies of this B state are higher than that of the A state. All of the lines between B and A comprise a system. So we have systems which are, and that's called rho by 1, for rotation, vibration, electronic. The combined change of rotational, vibrational, electronic states is called rho by 1 spectrum. Those are electronic transitions, and they tend to be have high energies, and therefore they're invisible or the ultraviolet. If we talk about changes only occurring between vibrational levels, those are less energetic, and they tend to be in the infrared. If you think about changes only between rotational states, there's not much energy involved, and they're in the microwave. Different techniques are used to study those different domains. So we're back to the pattern that I showed you a little earlier. This is what we took a picture of in our spectrum that we measured in our laboratory course. So we asked the students to identify these features. So this is a wavelength of around 570 nanometers up to about 610. And so they learned how to identify that this group of lines is so-called 6 to 2, meaning that these are lines in one electronic system, and they're grouped into different vibrational levels. So this would mean that the upper state vibrational level is 6 and the lower is 2. 7, 3, 8, 4. Notice how all of those deltas are 4, 4, 4, 4. So there's pattern, always patterns in spectroscopy. Difference in those vibrational levels is 4. And so you can interpret this pattern, and you can try to blow up this section using lasers and try to interrogate the populations of given quantum states. This is another example. This is a DC discharge that we do in my lab course. Basically, what I'm trying to get across is that we have now transitioned to 350 nanometers. That would be, so your eyes can see from around 400 nanometers to about 750. Shorter than that 400 we call the UV. Longer than what you can see, we used to call it the near infrared. So the terminology. So depending on where you look, you see different features. You might say at first glance it's really complicated. You break the problem into parts and you realize that eventually you track this down. There's some nitrogen lines and there's some OH lines. So over time, people have interrogated these things and figured out the pattern of lines that occurs. Now, if you wanted to measure the properties of the molecule and the quantum, the energy that dictate the molecule structure, you can use spectroscopy to determine the microparameters, or you can use microparameters to specify the spectroscopy. Okay, so but people, before lasers and before digital cameras, people used film. And so this is some examples from books, texts on radiation. It shows what happens if you record spectrum OH in a flame. So this would have been done in some laboratory flame. And that pattern of lines was isolated and identified as corresponding to a given pair of electronic states and vibrational states. Now, they used film, a piece of film, in the image plane of a device called a spectrometer or spectrograph. So they would look at a flame through a device and then spread the spectrum out, and then let the film expose the film. And that structure of that spectrograph led to these features. Now you begin to see why they call them lines. So there's no meaning to this vertical curve. The spectrum is spread out horizontally, recorded on a device with a slit. And so naturally they developed the terminology that these are lines. And each one of these lines corresponds to a specific wavelength, and therefore corresponds to specific changes in quantum states. And so here's patterns that they would observe for CH, NH, and so on. So in the early days, spectra recorded on the film. This would be emission spectra. But now we have lasers. So now let's look at emission absorption. This would be a classic experiment. We might have a laser, might be a small laser. It might have light that's propagated by an optical fiber. It might be collimated by some sort of a micro lens, and that beam might be passed across some sort of a laboratory onto some sort of a detector. These detectors are usually called quantum detectors. They're sensing individual photons. Photon comes in, and that photon is maybe converted to an electron, and that floats in the circle. That would be a quantum detector. Not all photons result in electrons. That's called quantum efficiency, but that's the method. So we might have a tunable laser here and adjust the wavelength and see what happens on this detector. Now, the fact is the lines that we see. So if you calculate the energy of a state and the energy of another state, take the difference, you get a number. But if you go to examine it in the laboratory, you can find out that what you get is actually a distribution. We call this the width of the shape of the line. So if you look really closely, you have to have high quality equipment to do this, or you have to use a laser. If we now measure the transmission as a function of wavelength, we might find that it has a shape to it. And if I convert that transmission to absorption, it's like this. So that, if the equipment is good enough, if we measure the actual line shape, we have to ask what does that depend on. And it can depend upon environmental parameters. So you might have heard of something called the Doppler, the collision broad alignment. So because the molecules are moving in space, and they're moving at specific at velocities described by the Maxwell-Boltzmann distribution, moving at a variety of speeds, then their emission or absorption of light is influenced by that motion. And so you get a little spread of the wavelength over which the emission or absorption can occur. That we call the Doppler. Or, because the molecules undergo collision, so a nitrogen molecule in this room is undergoing approximately 10 to the 9th or 10 to the 10th collisions per second. So it only lives around 10 to the minus 9, 10 to the minus 10 seconds before it has another collision. And because of that short time scale, because of what's called Heisenberg's uncertainty principle, if you start constraining how well something lives in time, then that corresponds to a broadening of certainty for energy. So if you specify something closely in time, then it's going to have an uncertainty of energy, vice versa. That's called the uncertainty principle. For those two reasons, these lines have shape. And because we now have the ability to study these shapes, we actually can infer some of the correct parameters. So we might use the shape, the width, to determine the temperature. But that comes to us from the Maxwell-Boltzmann distribution. Says that velocity is related to temperature. We might find a way to measure pressure. So the shape has become an opportunity for diagnostics. That's one of the things we do in my group is the shape of lines to characterize. All right. So we're going to focus a lot on this question of positions, shapes. And we start with positions. Positions we get by characterizing the energy levels of molecules and the allowed limits. Now, we do have to worry about how strong things are, and that has to do with the population density. So if we have a number density S of 1 at energy level 1, and here's energy level 2, the strength, which is often denoted by S, is going to be proportional to the number of molecules in this state. There's no molecules here, there's no absorption at this particular energy level. So we have to understand the Boltzmann distribution. The Boltzmann distribution says that the fractional population in level I, ratio of number density in I over the total number density of that species, is given by this relationship. G reminds energy of the K's here with Q, where G is called the degeneracy, epsilon is the energy of that state relative to some reference, and Q is the so-called partition function with some over state. So if you haven't seen that, you just have to accept the fact that this is a really important thing. This is the definition of temperature. In equilibrium, that is when temperature is defined, molecules will distribute themselves over their states in a way that depends on temperature. And that's the Boltzmann condition. So you know temperature, you calculate the distribution. If you measure the distribution, you just measure temperature. So this is the best way to measure temperature. Don't need this. So typically, if we're measuring temperature, we will look at the relative absorption in two different lines. Meaning we'll look at the relative absorption for two different bundle states. And that relative absorption leads us to the relative populations, which leads us to the temperature. So that's basically how we measure the best way to measure temperature. Okay, I'm going to lead you through a number of examples. You have to remember how long we're talking. I'm running a little bit. I'm going to zip through these. Okay, I'm going to give you some examples. I want to motivate the power of the process. This is thin-film dilator sensing for air propulsion. So I had this idea about 25 years ago. If we wanted to study aircraft or scramjets, we could take I call it a suite of lasers, meaning many colors. Lasers of different colors propagating by fibers from different parts of the engine, and interrogating that information in a way that gives us temperature, species, velocity, mass flux. So back in 1991, we came up with a scheme to measure the amount of air coming into an engine as a function of time. You know, knowing that air is comprised of oxygen, we can measure the velocity and the density of the air endpoint. So propulsion people want to know how much fuel is going in, how much air is going in, how much thrust is you get. That's what they want. So it's important to do. All right, so we've developed this capability over 25 years to measure a lot of different species and mass flux and so on. And we've taken these ideas to certain ground test facilities, and now for about 2 years ago, the Air Force actually flew this idea on the scramjet to try to measure what's happening inside the scramjet, propulsion parameters of the scramjet. So this is compact instrumentation that actually been flying. There's another example. This is now an example for near Stanford. There's a NASA laboratory called NASA Ames, and there they have 20 and 60 megawatt arc jets, which they use to heat the air, mostly air, to expand it to test the heat transfer of the shuttle piles on a shuttle. So they take high pressure gas, they add electrical energy, they expand it to high speed, and then they bring it to rest on some sort of heat transfer system. This is heavy duty experiment. It's all encased in big boxes, electromagnetic shields. One of these runs at 60 megawatts, one runs at 20, so it's a lot of power. The question is what's inside. So this is called constricted arc. It's several feet long, and they have an anode and a cathode. So the current is flowing down through here, heating this gas, and then it expands in a nozzle. The question is, if you wanted to calculate this flow, you'd say, well, what's the stagnation property? What's the stagnation enthalpy? What's the stagnation temperature? So they do heat transfer analysis to get the enthalpy, but it's best to actually measure the temperature correctly. So we try to do this. So we measured the time-resolved temperature by looking at the populations of the excited states of oxygen atoms. Take air, heat it to 7,000 Kelvin. The oxygen is dissociated into oxygen atoms. The oxygen atoms are distributed amongst their allowed electron energy states. If we measure those populations, we just determine the temperature. That's the idea. We've been doing this over maybe the last 6-7 years. So now if you talk about an atom, electronic structure of atoms, there's no meaning now from left to right. Energy is up, and there's notation. So there's a lot of notation in spectroscopy. But the point is there are different allowed transitions that can take place that correspond to different wavelengths. We wrote this transition right here. It corresponds to 777 nanometers, which is the wavelength for which we can buy lasers. That would be, it's kind of at the boundary between visible and near infrared. So we study that particular transition. And from this, we study the shape of that transition. That's the absorbance, that would be absorbance versus wavelength. It's actually comprised of several smaller features underneath. And from this area, we can get the number density of atoms in that state. It's like about 10 to the 10. Knowing that the oxygen is fully dissociated, knowing what the total pressure is in the system, we can use this population to get the temperature. And that's what we have to get the temperature. And here's an example. This is a plot of temperature versus time. This tunnel runs for quite a long time. Here's our temperature. We're measuring temperature about 67, 50 Kelvin. So the nice thing about spectroscopy is we really don't care what the temperature. We can do this at 10 degrees, we can do it at 10,000 degrees. You just have to pick states that are populated and find a place where the absorption spectrum is allowed. So it's a pretty good way to measure temperature. There's no thermocouple here, you have to use light. Okay, let's see. Okay, now I've got students working on pulse detonation engines, and we have a laboratory 75 miles away at the Naval Postgraduate School, and they have some sort of detonation engine. And the gas is choked and flows through a nozzle and flows out. And they would really like to know the time-dependent behavior of this detonation engine and how much energy is coming out. So we have instrumented this probe of this nozzle to try to measure water, CO, CO2, and from this to infer all the properties, including the enthalpy. So what you know about a converging diverging nozzle is that if the flow is choked, it's sonic at the throat. So you know the Mach number is 1. Speed of sound is related to temperature. So to measure the temperature, you've got the speed, and that's how we're going to get to the mass flux of the moment flux. So I don't know whether this movie's going to play that when I do this or not. This is the system sitting right here. And probing, this is different variations of this tunnel. Probably not going to play here. is going to leak. And so the interesting thing about this tunnel is it looks out onto the golf course at the Naval Postgraduate School. So really quiet this thing. Quite a shock. Okay, so we make measurements here and we infer a lot about this tunnel. So given that we assume, we already elected bound, given that we assume it's Mach number 1, we measure some properties there, get the temperature, get the pressure, get the velocity, get the enthalpy flux. What they want to know is if they take that time-dependent flux of enthalpy into some sort of turbine, could you possibly come up with an energy system, a power system that combines definition and a turbine. The definition wave is attractive because it gets close to the thermodynamic limit of the constant volume combustor rather than constant pressure combustion. So there's some thermodynamic arguments for why they do this. So we measure temperature. Notice they get up to about 3,000 Kelvin, which is time. We've been up to 30 atmospheres. It agrees pretty much with CFD. Okay, so the students did this and they got the mass flow versus time, milliseconds. They then used their other measurements to get back to enthalpy flux. So this is in megawatts. So this is the instantaneous flux of enthalpy from cycle to cycle to cycle. So they want to get the time-dependent enthalpy flux for studies where this can be used with the turbine. Okay, one more. I've already kind of shown you this, so I'll show you one more. So behind reflected shock wave, and I want to show you the power of measuring multiple species versus time. This is a molecule called methyl formate. This is relevant to biofuels. This is the structure of that molecule. And we want to watch it decompose. So we heat it to 1400 degrees Kelvin and we watch it go away using laser absorption. We watch the appearance of carbon monoxide, we watch the appearance of methanol, and we watch the appearance of methane and CO2, and even formaldehyde. So, and the idea is that if we measure enough of these species, we're going to get closure to conclude that we've been able to measure essentially all of the oxygen atoms, which makes us feel good that we can understand what's happening at some point in time. This would be the first time it's ever been done. Okay, so that brings us to the end of lecture 1. It's kind of background, motivation, setting the stage. Now we're going to launch into the spectra of diatomic molecules. We're going to look at rotation and vibration. I think I'm about time.